let me discuss the question of measurement of thermal properties of a cylindrical lithium-ion cell first. I think it's a good, interesting topic. It's experiments oriented, and so that is also helpful. And so we'll spend the time that it takes for us to discuss radial measurements, cylindrical cell measurements, and in the time remaining we'll go back and we'll talk about a few issues related to thermal modeling. Okay. So just a background, in the previous lecture we had talked about measurement of thermal properties of a prismatic lithium-ion cell, and towards the end I had shown the difficulties. I discussed the difficulties in measurement of thermal conductivity, radial thermal conductivity of a cylindrical lithium-ion cell. So let's talk about how we can measure the thermal conductivity of a cylindrical lithium-ion cell, where I can only place a thermocouple on one radial location. I cannot drill a hole and put a thermocouple inside. Okay, all right. So I'm going to close this and I'm going to start a new sheet. And that would be lecture number 8. Is that right? Thermal measurements continued. So here is a cylindrical lithium-ion cell. I'm showing a cross section. Actually, it's much better without the ceiling fans. Yeah, much easier to hear and all that. I place a thermocouple here. Okay. I cannot place a thermocouple in the center, so let's skip that for now and see where we go. Right. In addition to that, I wrap a heater all around the cell. And then on top of all this, I place insulation, heavy insulation. And then I take this entire setup and put it in a vacuum chamber. Okay. Remember that according to Fourier's law, QR is negative KR del T del R, and we used a relationship like this to find out the thermal conductivity of the prismatic cell. But there I needed to have two measurements of temperature. Here I will only get one measurement of temperature, and therefore this by itself will not take me too far. Right? I've got to think of something else with which to somehow extract the thermal conductivity of the cell from this measurement. Right? For that, I think it is easiest for me to go to the paper that we wrote and follow along. Okay? So this was the first paper we wrote in the area of lithium-ion batteries, continues to be the most cited and one of my favorites. And so let's see what we had done. So yep, this is sort of, by the way, how this is how a lithium-ion cell looks like. If you cut the cap open, this is a very tight toilet paper roll of the 5 sheets that we were talking about: anode, cathode, separator, current collector, etc. Those are very tightly wound and placed inside in a bath of electrolyte. The electrolyte is gone now, of course. These things jutting out are the current collectors that were supposed to touch the cap of the cell to make a connection. All that is gone, and this is how it looks like. The first time we saw the structure of the cell, the first thought that came to our minds was, okay, if I am a piece of heat here and if I am trying to travel outwards, then I am going to have to jump from one material to the other multiple times. How many times? Hundreds of times, right? Going from here to here, there is one material, then the next material, so I have to jump to the next one, and then I have to jump to the next one, and so on. Every time I jump, there is a resistance, right? It's like the contact resistance. It is indeed the contact resistance, right? So that provided us some thought, so a hypothesis, if I may say, that the thermal conductivity in the radial direction might be very different from the thermal conductivity in the axial direction. If you were traveling in the axial direction, you can just travel along these sheets, right, without having to jump from one sheet to the other. Whereas in the radial direction, you don't have a choice. You have to make these jumps again and again and again. So that was our motivation for measuring not only the radial, but also the axial thermal conductivity of the cell. Okay. So, like I was discussing, we took a cylindrical lithium ion cell. Oh, come on. We took a cylindrical lithium ion cell, placed a thermocouple bead at the outer surface, and then placed a heater around it. This is a thin heater, Kapton heater, also from Omega, if I remember correctly. And that is the hand of Stephen Drake, probably. Yeah. And then we put insulation tape around it, and on the two edges, the two faces, and so on. And then we placed it inside a small vacuum chamber. So this is a makeshift vacuum chamber. We basically drilled a hole to carry all the wires in and out, and then from here, you can't see it completely, but from here we pulled air out to create vacuum. I don't remember the number. I think it was minus 80 kilopascals or something like that. This is plastic. This equipment is actually called a desiccator. We didn't have a proper vacuum chamber in our lab. Yeah, so a desiccator is basically a piece of equipment. Yeah. So in material science, where is the enter button? In material science, there you go. It's essentially a vacuum chamber, roughly. It is used for drying materials. So if I have a wet material, I want to pull out all the moisture. I'll put the material in here. I'll connect this to a vacuum line, and I'll pull all the air out so that the moisture has no choice but to evaporate. I had used this for something else many years ago, and we said, okay, a desiccator is as good a thing as any other in order to run these measurements. Yep. And these are not very expensive. I mean, 2,000 bucks. And of course, we had to figure out how to seal this and all that stuff, right? A fairly crude measurement. This is not a measurement that will win me the Nobel Prize, but it gives me the thermal conductivity of a lithium ion cell, which is all I want. I don't want the Nobel Prize. Okay? So going back here is my setup, right? I have a thermocouple measurement. Actually, I can close this other one. No, let me keep that. Let me show it here. So my thermocouple will give me a temperature measurement as a function of time, right? So if I was to plot T versus time of the thermocouple, I only have one thermocouple. Initially, that thermocouple is at 20 degrees C. And for your benefit, let me just draw the setup once more. Here is my cell, here is my thermocouple, there is a heater all around it, and there is insulation on the outside. What kind of T versus time should you expect to see? Can somebody help me with that? It will increase, and then Okay, so what is being proposed is that it increases and then reaches steady state. Does everybody, sorry? Steady state, yes. Does everybody agree with this, or does anybody have any other thoughts? Hmm. That's a good thought. A steady state is reached when there is a balance between heat coming in and heat leaving. In this case, if the insulation is perfect and if I'm continuously supplying heat, then where is the heat supplied going? It's not going anywhere. It's being absorbed by the material continuously. And therefore it turns out that the temperature as a function of time for this problem should in fact look like this. So Stephen carried out these measurements. At this point, in all honesty, we had no idea how we will measure thermal conductivity. Okay, we cannot put two thermocouples. I said, okay, let's just put one and take some measurements. So we started taking measurements without knowing how we will use that data to determine the thermal conductivity. Okay, and the first set of data that he shows me looks pretty much like this. What do we do with this data in order to find out the thermal conductivity of the cell was the question. Right? Sure, it keeps increasing forever, and at some point he has to stop the experiment too. Right? Before it gets too hot, he switches off the power so that it does not get extremely hot within about 20-30 degrees C, if I remember correctly. So how do I take this data and use this data to determine my thermal properties was the question. For that, we went back to the theoretical analysis of this problem. So I can write a mathematical, I can write this problem mathematically and try to solve it in order to predict what the temperature distribution should look like. This is what I measure, right? What should it look like is the question. So if I was to go back here, in this problem, if this is the radial direction, then given that it's a one-dimensional problem, the governing energy equation for this problem is given by 1 over r del by del r of r del t del r. There is also a k here, kr, equals rho Cp dt over dt. Remember when I was teaching fundamentals of heat transfer, I had given the governing equation for the radial problem. Because there is no theta variation, because there is no z variation, therefore this is the only term that survives, and therefore we get this. This is subject to two boundary conditions and one initial condition. What are the boundary conditions? The first boundary condition is that negative k dt dr must be equal to q double prime, or rather plus kr dt dr, where q double prime is the amount of heating that is produced in my heater. Okay, if I measure the current and the voltage, I have some idea of what q double prime should be, provided all of it is going inside the body. Okay, and the other boundary condition, this is at r equals r, and at r equals 0, del t del r must be 0. We also need an initial condition, so t must be equal to t initial at the initial time. Say I start running this experiment initially at 20 degrees Celsius. How do I solve this problem mathematically was the question. And so he and I sat down, banged our head here and there and read that book and this book, and ultimately we were able to figure out a solution for this problem. Okay, I will not go into the details of the mathematical derivation here. Let me just show you the final solution. The pen? No, not really. It's okay. Let me just let me just scroll down like this. So these are the equations that I just wrote, and it turns out that a solution for that problem is given by this. It's okay. It's all right. So a solution for the temperature rise as a function of r and time is given by three components: theta m, s, and w. Theta m is this, s of r is this, and w of r comma time is this. Three components. Let's look at all three of them one by one. The third component has an exponential of negative something times t. What that means is that as time passes, this quantity should become what? Should become what? What is e? Sorry? It decaying. It should become 0, right? E to the power negative of a large number is 0. So at large enough time, this third quantity I expect to become 0. Okay? So at large enough time, this equation is predicting that the temperature at any location will become, this is a constant number, right? I can put small r equals capital R, and this becomes a constant number, and this is another constant number times t. So what my theory is predicting is that as the time goes to infinity, my theta at the outer surface is expected to become equal to a plus b t. A straight line, right? So as soon as we saw this and we saw the experimental data, it brought us some satisfaction that the theoretical prediction of it becoming a straight line is being seen in our measurements as well. So that was the first validation that, yeah, I think we are along the right track. Moreover, let us examine these expressions A and B. What is A? A is the constant quantity. It is Q double prime over KR, and this will give me R square by 4 if I put small r equals capital R. So that will be R over 4 in the denominator. This is A. And B is 2Q double prime by rho Cp R. Correct? Can you look at A and B and tell me what should we do? How does A and B help us measure the properties of this cell? Yeah. You see, suppose I do a measurement, I wait long enough and it becomes a straight line. I can find out the slope of this line, B, and I can find out the intercept of this line, A, right? If I know the slope and the intercept, the slope has Cp in it. Everything else is known. And the intercept has Kr in it. Everything else is known. So this tells me that I can measure the radial thermal conductivity and the heat capacity both using the intercept and the slope of this curve respectively. Does that make sense? It's like killing two birds with the same stone. Single measurement with a single thermocouple, keep in mind.
Idea is so simple, but just by applying it, you can measure.
Yeah, I mean the idea is not very difficult, and honestly, the way this happened, we did not know all of this from the start. We didn't start this work knowing that this is how it will go. We said we have to put two thermocouples. Oops, we cannot put two thermocouples. So what do? If you don't know how to swim and somebody throws you in the water, what will you do? You'll start splashing around, right? And hopefully you will survive. That's exactly what we did. We said cannot put two thermocouples, can only put one thermocouple. So let's put one thermocouple and see what happens, right? Then we took the measurements and it turns out to be like this, and we said, okay, can we explain this based on a theoretical model? So we went on the theory side, and it took us a little bit to derive this expression for the temperature distribution. This is not a straightforward expression to derive, at least not for us. But once we did that, and once we saw that this term goes to 0, the rest of it is a straight line, that's when we were like, yes, this agrees with what we are getting from experimental measurements. And then the last line to connect was the fact that the slope and the intercept has information about the two thermal properties of the body. Yeah, that was our eureka moment. That yes, this method will allow us to measure two properties, not just one, at the same time. So I'll show you the experimental data and the theoretical model in one curve. And this is how that looked. No, sorry, not this, the next one. For now, forget about the bottom pair, just focus on the top pairs, right? The red and the black. These are two different types of cells, a 26650 cell and a 18650 cell. In both cases, I am plotting in red the radial the experimental measurements, and I am then plotting the analytical model. You can see that the experimental data has a bit of a curvature to begin with, but eventually it becomes a straight line, right? And by measuring the slope and the intercept of that straight line, I am able to get the values of the thermal conductivity and heat capacity of the body. And we do it for two different cells. In both cases, we get the same trend, that there is some curvature to begin with, but then it becomes a straight line. And if I measure the slope and the intercept of that straight line, that is all I need to make progress here. Okay? Sorry? You want to go more than 700 seconds? Yes. No, we waited sufficiently long, and we simply did not get any steady state. And by that time, you see, the initial temperature was about 25 degrees Celsius. Add a temperature rise of about 25, and my cell is now at 50 degrees Celsius, right? I don't want to heat up the cell too much more. The manufacturer said, remember, keep my cell between 20 degrees C and 60 degrees C. So as a matter of safety, we had already decided before the experiment that as soon as we reach about 50 or 55 degrees C, snap, the experiment is over. We don't want it to explode on us, right? That is the reason why we could not go on any longer. Yes?
If we heat it very slow, then we will have more defined better.
Correct, yes. But our motivation here was to finish this experiment as quickly as possible, because if you wait longer, then there would be more heat losses to the surroundings. So we thought, I don't know if this is right or not, but we thought that it makes sense to finish this experiment as rapidly as we can. Yeah? And through a bunch of trial and errors, see guys, this is the final data set. It looks very nice, clean, beautiful, but I can tell you that there are 100 such plots behind it that are not presented in the final paper, where nothing was working right? It takes a lot of hard work and trial and error, and going back home feeling defeated, and then coming back again next day full of energy, and then trying something else, and maybe that is working, maybe that is working. It's like a jigsaw puzzle. When you put the jigsaw puzzle together, it looks beautiful, right? But you have to also be cognizant of all the hard work that goes behind in putting the pieces together. Maybe this should fit with this, nah, maybe that should fit here, this, that, right? A lot of hard work did go behind these plots, which we don't show in our final papers and dissertations, right? It's not as straightforward as the way I present it. You know what I'm saying? We also had all kinds of doubts and questions, and what if we do this or what if we do that, before we settle down on something that we think works well. Did you have a question? Yes. So both of these boundary conditions are specifying a heat flux, right? What is your question then? Yes. Yes. Uh, yes. I don't know. I'll have to think about it a little more. Here, the problem is clearly well defined, right? This is a physically well defined problem that must have a unique solution. If the problem was not fully posed, then perhaps there may have been infinite solutions. But this equation is faithful to this physical setup. I can always put a heater around a cylinder, and then I would expect there to be a unique temperature distribution, right? I don't know why mathematically, I don't know how to prove that the solution is unique here, right? And I don't know fully about what you are talking about. If you have something to show me, I would love to see about this fact that if there are two flux boundary conditions specified, then the number of solutions is infinite. Okay, can we take it up separately, please? Okay. Yes. Correct. Yeah, so I'm plotting the temperature rise above ambient. That is why these plots start from 0. Okay. It is very common in the heat transfer community to plot delta T and not T itself. Okay, because the T is not important. You could be running this experiment in an ambient at 20, 25, you'll get the same result if you plot delta T instead. Okay, so this is how we measured the radial thermal conductivity of the body. We ran a similar experiment in the axial direction as well. So this was a schematic of our setup for the radial measurements. Heater on the outside, thermocouple here, and insulation all around. We ran a similar measurement by flipping the cell by 90 degrees. So now we put insulation around the cell, we heat from the top, and we put a thermocouple at the bottom. This problem is in principle similar to that one. We also derive a solution for this problem. That one is given on the next page, I think. And that one is also similar. It has 3 components. This component, because of the minus sign, will go away at large times. The rest of it is A plus BT. A containing Kz, the axial thermal conductivity, B containing Cp, the radial thermal conductivity. So by measuring the slope and intercept of temperature versus time, I can find out Kz and Cp. And that data was also shown in those plots. The other two curves, set of curves, are the axial measurements. And again, the axial measurements, in the axial case also, experiments and the model are in good agreement for both cells, and therefore we can get the properties of the cell in the z direction as well. Okay? The results are summarized in this little table here. Don't read too much into that, because I don't think the heat rate was the same in both cases. It may simply have been because we were providing more heating in the radial measurement than in the axial measurement. You know what I'm saying? Q double prime, in other words, was different in the two measurements. So I don't think you can compare the two apples to apples. Okay? I think if you read the paper in more detail, it may provide the actual value somewhere. Okay? So these are measurements of 18650 and 26650 cells. Remember the nomenclature. 18650 means 18 millimeter diameter, 65 millimeter height. So these two cells have both the same height, but one of them is smaller than the other. 18 millimeter and 26 millimeter, slightly, not much. They both have the same cell chemistry, and so we do expect both of them to have roughly the same properties. And so our measurements show that the heat capacity was more or less the same. The Kz's were also more or less the same, and the Krs are also more or less the same between these two cells. The most important thing coming out of these measurements is that the axial thermal conductivity was much larger than the radial thermal conductivity. To put this in the context of typical materials, copper is 400 watt per meter Kelvin, very good conductor of heat. Typical steels have thermal conductivity of this range. So in the z direction, the heat is able to flow very nicely, in fact. But in the radial direction, it has a lot of difficulty in flowing because of this very low thermal conductivity in the radial direction.
Can it be possible that because it's a steel which is thermodynamically sealed, can it be possible that whatever that we are measuring experimentally, it is showing the thermal conductivity of that steel only?
It is showing the thermal conductivity of everything. What I am, see, this model that I built assumes the body to be homogeneous, right? This equation, or rather the equation above it, does not account for the steel casing and the anode and the cathode and the separator and so on. It is all lumped together in one single homogeneous material. So the properties that we are measuring are the effective thermal properties of the entire battery, including the casing, the separator, the cathode, the anode, etc. If you wanted to measure the thermal conductivity only of the jelly roll, then you would have to take that jelly roll out of the cell or take it from the manufacturer before you even insert it into the casing and repeat this measurement on that jelly roll. So certainly the values we get have some contribution coming from the properties of the thin metal casing, no doubt.
Because we are taking from the analytical model.
Correct.
But the final output which we are getting, this is based on the experimental data which we are capturing.
Which is being done on the entire cell. Yes. So what that means is that any properties that you get from such measurements are not the properties of the jelly roll. They are the properties of the effective cell, considering everything. You know what I'm saying?
How you are heating, for radial heating, you have used the nitrogen.
Yes.
For axial heating,
For axial heating, we purchased a circular heater and we stuck it on one of the surfaces of the cell. So if you go to omega.com and look for Kapton heaters, they have heaters of all shapes and sizes, rectangles, squares, circles of different radii. So we just picked one which matched our radius as close as we could have, and that is how these measurements were run. Okay? Any other questions or comments? And the fact that the radial thermal conductivity of the cell is so dramatically different from the axial value has a lot of very interesting consequences. Imagine if I am a piece of heat in the center of the cell, and if you are interested in removing that heat, what would you do? What is the simplest thing you would do if I give you a lithium ion cell and ask you to cool it down? Blow air over it? Yeah, blow air over it. That air, what it is doing is that it is touching the outer surface of the cell, and any heat available on that outer surface is being taken away by the air, right? So what that means is that if you're a piece of heat in the center of the cell, in order to make your way out, you have to first get to the outer surface. It's like going to the US. There are flights leaving from New Delhi, but to be able to get to the US, I need to first go from Ropar to Delhi, right? By the way, do most people call it Ropar or Roopnagar? Okay, yeah, the government can do whatever they want. Oh, I'm being recorded, sorry. But everybody will do what they say, right? And this has happened all over the place. In Delhi, Gurgaon, right? Technically it's Gurugram or something like that, but who cares?
IIT Ropar, then you can.
Okay, all right, good.
Official name is
IIT
IIT Ropar.
Ropar, good, all right. So in order to get to the US, I need to first go from Ropar to Delhi, right? Once I get there, there is a lot of air flowing, and I'll be able to get to the US easily, right? I hope you see the analogy between the two. The difficulty here is for me to get from here to New Delhi. The thermal conductivity of the cell in the radial direction is so poor that it takes a lot of effort for the heat. Not much of the heat is able to get to the outer surface. And therefore, this poses a significant thermal management challenge for lithium ion cells. You can fly as many planes as you want from New Delhi to the US, but if people are not able to get from Ropar to Delhi, then how will they all leave? Right? Similarly, you can blow as much cold air as you want on the outer surface. If the thermal conductivity of the cell inside is so poor, then you won't be able to remove a great deal of heat. Another consequence of that is that this cold air that is going to remove heat will do a very good job of cooling the outer surface, but the inner core of the cell will continue to remain cold. Whoever got to Delhi, whoever was able to get to Delhi is able to leave very easily because there's a lot of air flowing. But the problem is a lot of people are stuck in Ropar. The analogy here is that heat transfer is very effective on the outer surface. Whatever heat there is on the outer surface gets removed very nicely. But most of the heat in fact is stuck inside the cell, and it is causing a rise in the temperature of the inside of the cell. That is a practical consequence of this poor radial thermal conductivity of the cell. To which a thermal engineer could say, okay, if the radial thermal conductivity is so poor, why not use the axial thermal conductivity to remove heat? Right? So Amritsar airport also has flights going to the US, the axial direction. Why don't we all get people to go to Amritsar and leave from there, right? The thermal conductivity from Ropar to Amritsar is much higher. Correct? Yeah, that's one problem. The Amritsar airport is closed. They are using it for something else. A typical cylindrical lithium ion cell, the top and the bottom surfaces have already been used for making electrical connections. They are the positive and the negative terminals. So even if the heat was able to get to the top and bottom, there's nowhere for it to go from there onwards. All the air is blowing over the radial surface, not at the top and bottom surface. This is the dilemma here. I have availability of good cooling on one surface, but I'm not able to get to that surface effectively. And the surface that I'm able to get to doesn't have good cooling. And I cannot possibly redesign the whole cell in order to make the two ends available to me. Yes.
There is no tap cooling. What it means that the connections there are.
Yes.
There's on the top and bottom of this, they are making the connection.
Yes, absolutely. Tap cooling, people have looked into it, but somehow it's not become very popular. I don't know why.
When we are going through the literature, there is a conventional cooling type of thing.
Yes.
They are using the cooling.
Correct.
But some of them are looking for tap cooling also.
Yes.
And it shows good results also. But I don't know what this is level or not.
Yeah. In the last 10 years or so, the literature on cooling of lithium-ion cells has literally exploded. Hundreds, if not thousands of papers. Which technology wins in the sense of getting into a product depends on a lot more things than just technology. Right? Just because one particular technology is superior to the others doesn't mean that that will be the one seen in real products. Right? But we do what we can do, and then what happens. Okay. Few other things that we showed in this paper are the following. We showed a comparison of the three possible scenarios of a lithium-ion cell. This is the real scenario where the radial thermal conductivity is 0.2, the axial is 32, as it should be, what we measured, right? Then we said, okay, suppose I did not have this information. Suppose I erroneously assumed that the thermal conductivity of the cell is isotropic and it is 32 watt per meter Kelvin in both directions. Then my simulation will actually show that the cell is quite cold, when in reality the cell is quite warm. It will lull me in a sense of complacency, right? It will say all is well, no problem, whereas in reality there is a problem, right? I don't want to do that. But on the other hand, if I assume the two thermal conductivities to be 0.2 watt per meter Kelvin, that is also not good, because then it is giving me a false alarm. Too much problem, right? It's saying, oh God, your cell is about to explode, whereas it really is not. It's okay, it's not too bad, right? So in one sense, over design, and in some sense, in the other sense, under design. Recognizing the fact that the two thermal conductivities are very different from each other is very important for coming up with the right design of the cell. Does that make sense? Any questions? Yes. We have provided a convective boundary condition, I think, on all the other sides of the cell, and we've assumed some heat generation rate. Let me see if I can find that information. No, I'm trying to see if we provide information about the heat generation rate in this case. No, we don't really do that. Sorry, I'm guilty of not providing all the information. Most people do that. Yeah? Any other questions or comments? The other thing that I'd like you all to notice here is uh, is the fact that the 5 components of the cell, 3, 4, 5, current collector 1, current collector 2, separator, anode, which is typically made up of carbon, graphite, cathode, which is a lithium salt such as lithium cobalt oxide, and this is some kind of a polymer. Remember, we said that the measurement of the thermal conductivity value we measured is effectively a contribution from all of them, right? So the effective thermal conductivity we measured was 0.2 watt per meter Kelvin. Let me write it down in big letters here. What are the thermal conductivities of each one of them? Well, current collector are aluminum or copper that have extremely high thermal conductivities, about 400 watt per meter Kelvin. What I am trying to do here is the following. Look, there are 5 resistances in series, 1, 2, 3, 4 thermal resistances, keep in mind. When resistances add up in series, the total resistance is governed by the one that has the highest resistance. In other words, if this is 1000 units and this is 1 and this is 0.1 and this is 10 and this is 0.05, which is the most important resistance here? The largest resistance. That is the one that I want to reduce if I can, in order to reduce the overall resistance. Right? The overall resistance is 1011.15. This is the one that is contributing most to the total resistance. I am trying to run a similar analysis here to figure out which one of these is contributing to the low thermal conductivity of the cell. Why is the thermal conductivity of the cell so low? Well, let's put some numbers. Copper or aluminum is 400 watt per meter Kelvin. Anode graphite is how much? Low or high? No, graphite is a very good conductor of heat. Graphite has very high thermal conductivity. If somebody could look it up, it will help. I don't know the exact number, but my belief is it is hundreds of watt per meter Kelvin, if not that. While we were doing this work, somebody else, David Cahill at UIUC, was busy measuring the thermal conductivity of lithium cobalt oxide. How much did you find out? Because he was also onto something. This looked like an interesting problem to him as well, and he said, okay, let me measure the thermal conductivity of lithium cobalt oxide, and he reported this number to be about 3 to 4 watt per meter Kelvin. 1500, yeah, so very high, very high. So far, which is the slowest step in thermal conduction? As this heat passes through, which material will offer the largest resistance to the flow of heat so far? The lithium cobalt oxide. It's going to pass through the copper, the graphite very nicely, right? It's going to have a lot of trouble passing through the carbon, sorry, the cathode. The last one here is the separator, the polymer, and we did not find any measurements, direct measurements on this material, and so actually Vivek Vishwakarma, who was from IIT Ropar, carried out those measurements himself. Maybe tomorrow, if there is time and interest, I can talk about it very briefly, but I want to talk about the other work that he had done in more detail. Anyway, long story short, this number was found to be 0.5 watt per meter Kelvin. So the slowest step in thermal conduction was through the polymer. However, what was surprising is that the thermal conductivity of the overall material was even worse than the thermal conductivity of the worst material. Yeah, that was surprising. Take 5 materials, put them in series, and somehow the effective thermal conductivity of the entire thing is even worse than the worst material in that series. It's like taking 5 students, putting them on a team project, and the performance of that team being even worse than the worst student on that team. Does that happen very commonly? Why? Because these 5 students don't know how to talk to each other, don't know how to work together in a team. They're working in all different directions. So their output is even worse than if I had given that project only to the worst student. Even that student would have done a better job, right? That is what is happening here. If this entire battery pack was made up of the worst material, the polymer, it would still have conducted heat better than when I gave it all these nice, highly conducting materials. Somehow the effect of adding these highly conducting materials went in the wrong direction. So we wondered about this for a while, and we thought about why this might be happening. And in fact, it was a good friend of mine who pointed this out to me, that look, what is happening here is that in addition to the resistances of these materials, when you put these materials together, there is resistance at the interface of these materials as well. So just like the example of that team of 5 kids, when I put those 5 kids together, in addition to doing the work themselves, they now have to talk to each other. The ideas have to flow from one to the other. And if they're not talking to each other, those ideas will not flow, and the performance of the entire team will be worse than the performance of single individual students. Here, the heat is able to jump very nicely across each material. But because this effective thermal conductivity is lower than this number, that gives us a hint that the heat is having difficulty jumping from one material to the other. Yes?
One more can be that we are having a liquid electrolyte and everything is porous.
Yes.
That will also reduce, and we don't know the electrolyte conductivity is also, I think, low.
It is low, correct, yes. The thermal
These are not completely solid materials.
These are porous materials, exactly. The electrolyte is everywhere.
And when we are generally when we go for the K, theoretically calculating the from thermal resistance.
Yes.
We don't consider the electrolyte.
Yes, absolutely. But nevertheless, this low thermal conductivity cannot be explained by the electrolyte alone, because the electrolyte also has decent thermal conductivity. If the electrolyte had a conductivity of 0.1, then I could say that yes, there's so much electrolyte, it's not passing through the electrolyte well, which is why I'm getting a low value. But even the electrolyte is larger than the effective value, right? That, with some help from a friend, gave us a hint that contact resistance at the interfaces in this problem is an important consideration for us. See, our motivation at the end of the day was to increase this number. I want this number to be as large as possible. We've already seen that. Remember, when we were doing theoretical analysis yesterday, we saw that increasing this thermal conductivity would dramatically reduce the temperature rise in the cell. So there is motivation in increasing that number. Now the question is, how do I increase that number? That number is already so low compared to all of these that quite likely increasing this number will not help. Right? Certainly increasing this number will not help, because this is not the rate limiting step. This is not the largest resistance. But even this resistance does not fully explain such a low value. right? And that is when, based on the insights we learned from my friend, we figured that we need to look at the contact resistances at the interfaces. We need to measure those contact resistances, and we need to see if those contact resistances in fact are the rate limiting steps in this process. Now the problem is that there are several contacts here. There is a contact between current collector 1 and cathode, a contact between cathode and separator, a contact between separator and anode, and then a contact between anode and current collector 2. So 4 contacts between these 5 materials. In principle, each of these contacts offers a contact resistance, and we have to figure out which one of these contact resistances is the largest, is the rate limiting step. Okay, that is the question that I will address in the first lecture tomorrow, where we will look at this contact problem in more detail, and we'll figure out which one of these is the rate limiting step. And once we find out which one of these is the rate limiting step, remember, what is our overall motivation? Our motivation is to increase this number, right? So once I find out what is the rate limiting step, I want to also figure out how to improve that step in order to increase the overall thermal conductivity of the cell, right? All of that was summarized in an excellent paper, again one of my favorites, led by Vivek Vishwakarma, who was an undergraduate student here before he came to my lab, and that is what will be the focus of our discussion in the first lecture tomorrow. Okay, for now, since we are past time, let's stop here and take a break for lunch. We will meet at 2 o'clock, and I will talk about a slightly different topic at that time. Okay, thank you so much.